Around the eastern Mediterranean, systematic breath-hold diving for sponges and pearls had been practiced for at least 2,000 years before the Common Era. The Scandalopetra, a flat stone typically weighing 10 to 15 kilograms, was not a crude improvisation but a precision instrument, shaped and weighted to carry a trained diver from the surface to the seafloor in the minimum possible time. The descent technique was refined across generations. The diver would grip the stone, hyperventilate briefly to flush carbon dioxide from the blood, plunge over the side of the boat, release the stone at the bottom, work for the seconds available, and ascend before the rising carbon dioxide level triggered an uncontrollable urge to breathe. This was a system. It worked within strict biological limits. Those limits were the problem. The human body is not built for depth. At 30 meters, a diver's lungs compress to 1/4 of their surface volume. Nitrogen dissolves into the bloodstream at elevated partial pressure, producing narcosis, an impairment that ancient divers described as enchantment, a feeling of being called to stay at the bottom. They were not wrong about the experience. They were wrong only about the cause. The cause was gas law, and gas law can eventually be engineered around. The first engineering response to the limits of breath-hold diving was the diving bell, a large vessel, open at the bottom, lowered into the water with air trapped inside. Aristotle described a device of this kind in the 4th century BC. The principle is elegant, and the limitation is severe. As the bell descends, increasing pressure compresses the trapped air, enriching it with carbon dioxide exhaled by the divers breathing from it. The bell bought time. It did not solve the problem. Solving the problem required a sealed structure, a wall that pressure could not penetrate. Around the eastern Mediterranean, in the Aegean and Ionian seas, systematic breath-hold diving for sponges and pearls had been practiced for at least 2,000 years before the Common Era. The Scandalopetra, a flat stone typically weighing 10 to 15 kilograms, was not a crude improvisation, but a precision instrument, shaped and weighted to carry a trained diver from the surface to the seafloor in the minimum possible time, preserving as much of the breath hold as possible for actual work at the bottom. The descent technique was refined across generations. The diver would grip the stone, hyperventilate briefly to flush carbon dioxide from the blood, then plunge over the side of the boat, riding the stone straight down, releasing it at the bottom, working for the seconds available, and ascending ideally passively, with the residual buoyancy of the lungs assisting the return before the rising carbon dioxide level in the blood triggered an uncontrollable urge to breathe. This was a system. It worked within strict biological limits. Those limits were the problem that 2,000 years of engineering would struggle to transcend. The human body is not built for depth. The physics is straightforward. As a diver descends, the increasing water pressure compresses the lungs, reducing their volume at 30 meters. A diver's lungs are compressed to 1/4 of their surface volume. The nitrogen in the lung air dissolves into the bloodstream at elevated partial pressure. At depths beyond 30 meters, that dissolved nitrogen begins to produce narcosis, an impairment of judgment and perception that ancient divers described as a kind of enchantment, a feeling of being called to stay at the bottom. They were not wrong about the experience. They were wrong only about the cause. The cause was not magic. It was gas law. And gas law, unlike magic, can eventually be engineered around. The first engineering response to the limits of breath-hold diving was the diving bell, a large vessel, open at the bottom, lowered into the water with air trapped inside by the surrounding water pressure. Aristotle described a device of this kind in the 4th century BC, noting that it could be lowered to divers working at depth to allow them to breathe from the trapped air before ascending. The principle is elegant, and the limitation is severe. As the bell descends, the increasing water pressure compresses the trapped air, reducing its volume and, eventually, enriching it with carbon dioxide exhaled by the divers breathing from it. The bell bought time. It did not solve the problem. Solving the problem required understanding that the only permanent answer was a sealed structure, a wall, that pressure could not penetrate. And building that wall was an engineering challenge that would not be solved another 15 centuries. The armored diving suit appears in the engineering literature of the medieval and early modern period repeatedly, always with the same ambition and the same catastrophic limitation. Leather suits sealed with tar, articulated iron shells with small glass viewports, brass helmets connected to surface air pumps through leather hoses. Each iteration was an attempt to carry the surface atmosphere down to depth in a wearable container, a personal pressure vessel wrapped around a human body. Each iteration failed, in different ways, and at different depths, for reasons that were increasingly well understood, but technically impossible to solve with the materials and manufacturing capabilities available. The fundamental problem was the joint. A sealed diving suit is only as watertight as its weakest connection. The point where the helmet meets the suit, where the glove meets the sleeve, where the viewport glass meets its metal frame. At shallow depth, the pressure differential across a poorly fitted joint is small, and a small leak is manageable. At depth, the same joint must resist forces that scale directly with depth. At 30 meters, the external pressure is 4 atmospheres, 4 times the force per unit area that a surface-level seal must hold. Medieval craftsmen could not achieve the tolerances required for reliable sealing at depth. The water found every gap. Divers who went deep in these suits either ascended rapidly or did not ascend at all. The Industrial Revolution changed this calculus entirely. Precision casting, standardized thread forms, vulcanized rubber gaskets, the manufacturing infrastructure that emerged through the 18th and early 19th centuries, produced components with dimensional tolerances that medieval craftsmen could not approach. The standard diving dress that reached its mature form by the mid-19th century, the copper helmet, the canvas suit, the lead-weighted boots, the hand-operated surface pump, delivering continuous air through a hose, was not elegant by modern standards, but it was reliable within its operational envelope, and that envelope was sufficient for most practical underwater work: harbor clearance, salvage, cable laying, and the inspection and repair of underwater structures. The constant volume suit represented a deeper engineering insight than the standard diving dress. Standard diving dress exposed the diver's body to the pressure of the surrounding water through the suit material, requiring the diver to breathe compressed air at ambient pressure and exposing them to all the physiological hazards of pressure exposure. A fully rigid, articulated shell maintained a fixed interior volume regardless of external pressure, keeping the diver's body at 1 atmosphere regardless of depth. The concept was sound, and the engineering challenge was formidable. Every joint in the articulated shell must move freely through the range of motion required for work, while maintaining a pressure seal against the differential between internal and external pressure that increases with every meter of descent. That challenge would not be reliably solved until the mid-20th century, when materials science and precision manufacturing had advanced far enough to build joints capable of both. William Beebe and Otis Barton descended into the Atlantic in 1930, inside a hollow steel ball. The bathysphere was not streamlined. It was not self-propelled. It was not maneuverable in any meaningful sense. It was a hollow steel ball, attached to a cable, lowered from a surface ship, and it reached depths 923 meters on August 15, 1934, that no previous human-occupied vessel had ever approached. It held together at those depths because of a geometrical principle that the engineers who designed it understood precisely. A sphere distributes compressive hydrostatic load evenly across its entire surface. Under uniform external pressure, the forces on a spherical shell resolve into circumferential compression in the shell material, a loading condition that steel resists exceptionally well, with no corners or flat sections where stress can concentrate and initiate failure. Every serious deep-sea pressure vessel that has followed the bathysphere has used a spherical or near-spherical pressure hull for its inhabited compartment, not because the sphere is convenient to manufacture or easy to fit out internally, but because the physics of deep-sea pressure demands it. The viewport represented a separate and persistent engineering problem. Fused quartz, the material Beebe and Barton used for their conical viewport plugs, is transparent, which is why viewports exist, and it is substantially weaker in tension than the steel hull into which it is fitted. Under external pressure, the quartz cone is driven into its conical seat in the steel hull, and the compressive forces in the quartz are large and well distributed. The design was a specific solution to a specific constraint. Use the external pressure itself to drive the viewport material into a geometry that places it in compression rather than tension. It worked. The seals held. Jacques Piccard and Auguste Piccard's Bathysphere concept, eventually realized in the Trieste, solved a problem that the bathysphere's cable attachment could never resolve. The cable limited depth by its own length and strength, rather than by the structural capacity of the sphere. The bathyscaphe achieved free movement at depth by using a float filled with gasoline, a liquid less dense than seawater, and effectively incompressible, to provide the buoyancy required to keep the vehicle neutral or positively buoyant. To descend, iron shot ballast was attached. To ascend, the iron shot was released, and the gasoline float provided the upward force. The Trieste descended to the floor of the Challenger deep, on the 23rd of January, 1960 to 10,916 meters, the deepest point in the world ocean, and returned its 2 occupants to the surface intact. The ocean was, for the first time, demonstrably accessible to humans at any depth. Titanium changed deep-sea engineering, the way alternating current changed electrical distribution, not by doing something entirely new, but by doing the essential thing so much better that the entire system could be redesigned around it. The metal is not the strongest material by absolute measure, but it combines high-yield strength with low density and, critically for any structure immersed in seawater, with near-perfect corrosion resistance. A steel sphere of equivalent pressure rating to a titanium sphere would be substantially heavier, consuming buoyancy that must then be provided by additional flotation material, cascading into a significant engineering penalty. DSV Alvin's titanium personnel sphere, introduced in 1973, gave a crew of 3 access to depths of 4,500 meters, roughly the average depth of the world ocean, within a vehicle that the surface ship could reasonably handle. The sphere's walls were approximately 50 millimeters of titanium alloy, machined to precise spherical tolerances, and assembled from hemispherical forgings. At 4,500 meters, the external pressure on the hull's exterior surface exceeds 450 atmospheres. The sphere holds because the yield strength of the alloy, the precision of the forgings, and the geometry of the shell combine to keep every point in the structure below the material's failure threshold. The implosion of the Titan submersible on the 18th of June, 2023, illustrated the consequences of not knowing where that threshold was. OceanGate's vessel used a carbon fiber cylinder as its primary pressure hull, a material that offers exceptional performance in tension, but whose behavior under repeated compressive cycling is more complex and less well characterized than the steel and titanium alloys that have been standard for crude deep-sea pressure vessels for decades. Carbon fiber laminates, subjected to repeated compressive loading, accumulate microscopic damage at the interfaces between fiber layers, delamination that is difficult to detect visually, and requires acoustic emission monitoring to track with any reliability. Each pressurization cycle degraded the hull further. The accumulated damage was not caught. The hull failed catastrophically at depth, killing all 5 people aboard in milliseconds. The investigation that followed accelerated the development and adoption of acoustic emission monitoring protocols for composite pressure hulls across the deep-sea engineering community. The autonomous underwater vehicle has progressively displaced the human-occupied vehicle for the widest range of deep-sea research missions, not because the engineering of crewed vehicles has reached its limits, but because the absence of a crew eliminates the most demanding engineering constraint in the design, the requirement to maintain a habitable pressure sphere with atmospheric composition control, thermal management, and the structural mass that all of that requires. Liquid breathing is not science fiction. Perfluorocarbon liquids dense, oxygen-rich compounds that can dissolve sufficient quantities of oxygen and carbon dioxide to support mammalian respiration have been demonstrated in animal subjects since the 1960s, and the underlying physics is well established. A diver breathing oxygenated liquid perfluorocarbon rather than compressed gas would experience no pressure differential across the lung walls, because the liquid filling the lungs would be at the same pressure as the liquid surrounding the body. The hydrostatic force that crushes air-filled voids at depth would become irrelevant to pulmonary function. The lungs, filled with an incompressible liquid, would be in pressure equilibrium with the ocean. The engineering challenges that remain are substantial. The metabolic cost of breathing a liquid is significantly higher than breathing a gas. Carbon dioxide removal from a liquid breathing system requires external support, and the transition between gas and liquid breathing is physiologically demanding. But the physics that would make liquid breathing possible at any depth is not in question. The material science challenge is not whether it can work, but how efficiently and safely it can be implemented for extended operational use. Soft robotics offers a fundamentally different approach to the pressure problem, not resisting deformation, but accommodating it. A rigid pressure hull survives depth because the engineering of its shell keeps external pressure from reaching the interior. A soft robot survives depth because it has no interior in the relevant sense. Its body deforms under pressure, the way that deep-sea organisms do, with no sealed gas-filled void that the ocean can collapse. The electronics that require protection are housed in compact, purpose-designed pressure vessels or in pressure-tolerant oil-filled housings. The actuators that move the robot's limbs are hydraulic or pneumatic systems operating at ambient pressure. The vehicle can, in principle, descend to any depth without the exponential engineering cost that comes with scaling a rigid pressure hull to resist ever greater hydrostatic loads. In 2026, soft robotic vehicles are conducting survey operations in the Hadal Zone at a fraction of the operational cost of conventional deep-sea vehicles. The 75% of the ocean floor that has never been imaged at useful resolution represents the largest unmapped terrain on the planet. Artificial intelligence is transforming the economics of closing that gap, coordinating fleets of small autonomous vehicles, adapting survey paths in real time based on incoming data, directing vehicles toward features of interest and away from areas already characterized, achieving coverage rates that no single vehicle and no human-directed operation could approach. 2,000 years after the first sponge diver clutched a flat stone and plunged into the Aegean, humanity has crossed a threshold in its relationship with the deep ocean. The abyss is still dark. The pressure at the floor of the Mariana Trench is still 8 tons per square inch, but it no longer wins by default. The engineering, at last, is catching up.